We may have just detected the most promising signs yet of a possible clue that there is life outside the solar system. Using data from the James Webb Space Telescope, the astronomers led by the University of Cambridge have detected the chemical fingerprints of dimethyl sulfide and dimethyl disulfide in the atmosphere of the famous Earth's twin exoplanet K2-18b, which orbits its star in the habitable zone. Hello everyone, welcome back to PhysxX, and today we'll be discussing about a discovery that may be your childhood dream. The story begins in 2015 when NASA's Kepler Space Telescope first spotted a faint dip in starlight as a planet passed in front of its host star K2-18. This discovery, catalogued as K2-18b, revealed a world unlike any in our solar neighborhood. Roughly 2.5 times the radius of Earth, K2-18b falls into the sub-Neptune category, a class of planets without precedent close to home. Yet its orbit, a swift 33-day dance around the cool red dwarf, places it squarely in the star's habitable zone, where liquid water might persist. Interest in K2-18b skyrocketed in 2019 when astronomers using the Hubble Space Telescope detected telltale signs of water vapor in its atmosphere. Suddenly, these strange hydrogen-rich worlds became a prime target for the next generation of observatories. That's when scientists got their hands on the James Webb Space Telescope. Armed with instruments capable of dissecting light in exquisite detail across a wide swath of infrared detail. With JWST's near-infrared imager and slitless spectrograph and the near-infrared spectrograph, researchers confirmed the presence of methane and carbon dioxide, key carbon-bearing molecules, in what came to be envisioned as a Haitian world, a vast ocean enclosed under a hydrogen canopy. Still, water, methane, and carbon dioxide, while exciting, can all be produced by non-biological processes under the right conditions. The real breakthrough came when Professor Nikku Madhusudhan and his team at the University of Cambridge turned JWST's mid-infrared instrument MIRI towards K2-18b for a longer, more probing look. In observations covering the 6 to 12 micron range of the spectrum, they identified spectral features that could be explained only by two compounds, dimethyl sulfide and dimethyl disulfide. On Earth, DMS flows from the metabolism of marine microorganisms, primarily plankton, and DMDS follows as it oxidizes. There is no known abiotic chemical pathway that produces these gases in significant quantities. To detect these molecules in the atmosphere of K2-18b at all is extraordinary. To find them at an estimated abundance 20 times greater than our Earth is quite simply startling. The team reported the signal at a 3 sigma significance level, a statistical way of saying there is only a 0.3% chance that the finding is a fluke. Yet, in the rare field language of scientific discovery, 3 sigma is compelling but not conclusive. The gold standard is 5 sigma, which corresponds to a 1 in 1.7 million chance of error. To reach that threshold, Madhusudhan's group estimated they will need roughly 16 to 24 hours of additional JWST observation, an investment in telescope time that major observatories guard jealously. If granted, this follow-up could transform the tantalizing hint into a slam dunk detection. Of course, extraordinary claims demand extraordinary scrutiny. Skeptics caution that we must rule out every conceivable non-biological source. Could volcanic activity on K2-18b spur sulfur compounds skywards? Might photochemistry driven by the red dwarf's erratic ultraviolet flares create false positives? These are the questions planetary scientists are racing to answer. Laboratory work on sulfur-bearing molecules under exotic conditions is underway, and atmospheric models are being tweaked to explore all possible abiotic scenarios. Meanwhile, the concept of Haitian world has captured imaginations far beyond academia. First proposed in 2023, Haitian planets represent a new habitable category, ocean worlds larger than Earth. wrapped in hydrogen-rich envelopes that could sustain life in warm surface waters. K2-18b became the poster child for this class, demonstrating that even planets dramatically different from our own may host ingredients for life. Reflecting on this trajectory, the Kepler's discovery to Hubble's water detection, from JWST's carbon fingerprint to the potential sulfur biomarkers, one sees the revolution of planet science in microsm. Each technical leap opens a new window on the universe, revealing complexities we should scarcely imagine. In under a decade, we have gone from finding distant worlds to probing their atmospheres for gases of life. What lies ahead? If JWST confirms DMS or DMDS at 5 sigma, K2-18b will join a select club of planets bearing the strongest signs yet of life beyond Earth. Future observatories such as ground-based extremely large telescope in Chile or the proposed LUVOIR and PHysxX space missions could capture direct images and spectra of such worlds, mapping clouds, oceans, and possibly seasonal changes. Advances in laboratory astrophysics and atmospheric modeling will sharpen our tools for distinguishing life's signature from nature's mimicry. And yet, even if K2-18b falls short of definitive proof, the very act of searching refines our understanding of what makes a planet habitable. Every spectrum we record, every molecule we identify, informs a more nuanced portrait of distant worlds. We learn not just where life might arise, but how it might express itself under alien suns. Back on Earth, each new finding stirs public imagination and philosophical debate. Are we uniquely or merely one example in a galaxy teemed with life? Does the emergence of simple microbial ecosystem on a Hycean world mirror an early chapter in our planet's saga? And if life does take hold in hydrogen-rich seas under the red dwarf skies, what adaptation might those organisms evolve, and could we ever recognize their biochemistry? The quest for life beyond Earth is no longer confined to imagination. It is unfolding in real time. With every photon captured by JWST and every spectrum decoded, we stand on the brink of answering a question as ancient as human curiosity itself. As the hour to follow-up observations mount and as next-generation telescopes come online, we edge over closer to a discovery that will resonate across science, culture, and the human spirit. So, the next time you gaze skywards, remember this. Somewhere out there on a world once invisible to us, tiny creatures may be exhaling gases into the twilight. And here on our blue planet, we are listening, eager for the faintest echo of a distant song that might tell us we are not alone.